Good evening. My name is Carlos Munoz, and today we're presenting the Integrated Subsystem Test Review for Aero. Introduce yourself, guys.
My name is Dario.
I'm Nathaniel.
I'm Ollie.
My name is Luca.
And I'm Aziz.
My name is AJ.
To start things off, this is the ISTR presentation outline. We'll be going over the action items, mission overview, system overview, updates of the subsystem testing results, integrated subsystem testing results, plans for FMSR, updated submarine test plan, updated WALPS test plan, project management, conclusion, next steps, and of course, questions. To start off, our action items. We have already sent all the address and phone numbers to deliver the power connector and the deck plate, and we have received everything. The payment status has been fully paid. We sent the receipt not too long ago, and we have our CAD stuff as well. The manufacturer picture has been sent. We included our LED to our PCB board. It's included on slide 45, and integrated inhibitor included on slide 61. So mission statement, the Aero mission statement. Our NJIT mission is to design and demonstrate a dual-stage suborbital platform, Aero, which utilizes stationary payload Overwatch as a central hub to deploy Scout. Together, these systems will characterize the ionosphere by measuring electron density and analyzing the dynamic forces experienced during reentry.
So some changes that we've made so far, specifically for Scout, I remember we were talking to you about this, Wesley, was the material chosen for Scout and for Overwatch. We're thinking of choosing a glass fiber infused PPS. There's multiple benefits for this. One, it makes Scout lightweight, it has a good thermal resistance, and RF transparent. That is really crucial for us with the rock blocks sending signals over, and also with thermal resistance, it was a good choice. And then going more further in, these are just some more pictures of Overwatch that we wanted to 3D print and of Scout in the assembly. And then, like I said, this is just more of us choosing the 3D printed filament. And yeah.
The Lambda probe has undergone some changes. We are now also using PBS for the case. It was originally going to be machined aluminum, but it was not necessary. Also, this way it is more, there's better isolation. First prototype has been built. We have ceramic aluminum sleeves, 2 tungsten rods with 5mm separation, and we're doing a positive to negative 10 volt sweep, no longer 50 volts. So we're not using high voltage.
This is the electrical subsystem overview. These are unchanged from previous presentations. This is the Overwatch, which is a zoom in, same thing. Scout's also the same thing. So basically, there might have been minor changes in the architecture, but the general flow of the boards still remains the same.
As a manifest location and detail confirmation, the physical integration of our deck is letter F. Our subsection is assigned as experiment 3 in system 2. We're located on the deck plate F with Nebraska as well. And we're using the GSE 2 line at T-minus 45 and a timer event 2 line at T+160 seconds. Just another overview of our RockSat manifest as of January 23, 2026, including the ejection confirmation, which is the next slide. So deployment vectors, we're heading in the direction of going west in orientation 180 degrees. Deployment will be at T+160 seconds using timer event 2, and ejection type will be spring loaded.
The timer event matrix is unchanged from STR.
All right, in the design specifications, for Overwatch, it's mostly stayed the same. It became a little bit lighter since the cam mount is now made out of PPS. Same with Scout. Scout is a little bit lighter since it's now made of PPS. Nebraska's weight went up once we got their bill of materials and their CAD models. So overall, we are under our 15 pounds by 3 pounds for the most part. And then for the design specifications, this is mostly unchanged from the STR. The only change here is the Lambda probe voltage. Instead of 50, it's now 10 volts, but it's about the same amount of battery used for the rocket.
The design specification for the pin assignments are unchanged. We are still using 9 and 10 to power on the experiment and then deploy it at T plus 160 seconds.
And then for user guide compliance, it's about the same. Everything is the same except for using our 28 volts. We are staying under 28 volts. We're only be regulating down to 5 for the Arduino and components, and then the 10 volts sweep for the Langmuir probe, and then the RF signals for the XP and the rock block.
So special requests. This was the same as last time. We fully successfully integrated Big Red with Arrow, even with their new designs. Not really much change from their designs. I think they just chose lighter standoffs. If you go to the next slide, you can see this is just the standoffs were just a bit thinner. I think they chose aluminum ones. Not that many changes. And then subsystem test results. We were manufacturing, and we saw for Scout. This is the setup for Scout, and for Overwatch as well. Everything put together. We're testing the stepper motor here to see if it will work with our gears. So the stepper motor in the corner over there would turn the worm gear and would open up Scout to launch.
All right, and then for Overwatch, our overall design specifications, the next steps for the test will be mounting to wall deck with flush countersunk bolts and nylon locking nuts. We already have the bolts. The nuts are ordered. They should have been here today, but they'll probably be here tomorrow. We'll connect to wallops and Scout using mil-spec connectors. 3D printing the cam holder and cam rings, complete post-fabrication finishing, sanding and nailing any of the 3D printed parts, complete assembly in flight configurations, 3D printing. We were going to 3D print the Big Red sat just for final placement, but since they're going to send it to us, I guess we don't have to do that anymore. The big changes, material changes from aluminum 6061 to fiber on PPS. We optimized the stepper motor mount just to get more strength, and we created guides for Scout to deploy so the 3D printed parts don't crack under the load. And then for the springs, we have confirmed 10 inches per second. And then for the fully labeled model here, it's mostly the same. Not much has changed. Just some of the parts have changed internally. And then this is just better pictures, more of our gears.
So a quick status: we completed an Overwatch fitment check using a cardboard prototype. We have successfully completed Overwatch assembly using the cardboard prototype and stepper motor assembly as well. We're waiting for the PCB board to arrive. We ran a stepper motor test run. We executed and verified full release of the cam ring mechanism.
So mechanical integration test, the results that we got from it, it was a success. All the parts were moving from the stepper motor to both the gears moving, and then also the cam mount system moving and the cams themselves moving, so Scout can eject. All the gears meshed together. There wasn't a problem that we've had with that. What's not final is that we're waiting for the PCB boards to arrive, but we did everything via breadboards and Arduino, and everything worked out smoothly. This is just more. These are just some videos of the stepper motor.
The IMU.
Yes,
The IMU and
Just a quick thing to know. So this simulates the first board completely. So it uses the regulators and everything just to verify that the whole circuit works when they're all connected to the Arduino.
So now this is mechanical integration with our prototyping. So with the L bracket, we decided to water jet it, but to check if our tolerances and our measurements were right, we just did a quick mock-up on a laser jet with some flat piece of wood, made sure everything was good. Once we saw that everything was all right and it was ready to go, we put it into the water jet. We made some things where we made our diameter smaller, just some post-processing things to make sure everything fit. Welded everything up, both the L bracket and the spring mount holder, as you can see here. And here's some pictures of that cardboard prototype and also in the laser jet. And then this is the final product from the water jet. As you can see, the video of the water jet cutting the L bracket and everything else.
So going into the stepper motor, last time we just did a CMake simulation on our own devices, but now we're actually validating the Arduino and actually using the DRV drive, where we're driving any NEMA stepper motor for the full camera release. Obviously, the requirements are for the confirming the closed loop encoder feedback and ensure the worm gear doesn't prevent any backdrive under load, and we don't want it to be snapping under pressure as well. So from the testing results, like you just mentioned, we verified the accurate counterclockwise and clockwise angular displacement across multiple step counts, which you have mentioned, like 50, 100, 200, 400. The speed, we're trying to consistently and maintain 180 full cam release with less than 1.8 seconds per cycle. We are validating the possibility positional accuracy with encoder feedback, matching expected steps with tolerance, repeatability, flawless executed 25 consecutive deployment cycles without degradation. Like mentioned, we're trying to have a consistency throughout the system. The next phases will be the SIT, and we'll most probably execute the full deployment sequence with Scout payload loaded into the flight configuration on the Overwatch assembly for the future, especially.
As for the final phase of Overwatch, some tests that we're going to run during now until the FMSR would be a deployment system final testing, spring-loaded deployment tests, locking cam nodes, stress tests, PCB communication testing, and software full mission simulation tests as well. Overwatch is currently not final. We are still waiting for electrical components to arrive, like PCBs and connectors. We're also waiting on the spring to arrive. It should have arrived today, but it hasn't arrived. So there's a few things that we're waiting for to finalize all our tests before the FMSR.
All right, and then this is the Scout, mostly unchanged. Inside, there's some internal geometry that has changed just because of the filament. We did a more dynamic wall, so we have thicker walls where the stresses are higher. The next steps is fully manufactured and assembled Scout. We will connect mechanically to Overwatch using multiple cam system. That didn't change. Electrical connection we made using magnetic pogo pins or other type of pins. I think that might be changed. For changes, updated mount solution for Langer probe, antenna, and pogo pins. Major material changes for the back end. The back end is going to be aluminum. It went from aluminum to the 5-round PPS GF20. And another note about that filament is it is not conductive like aluminum or any carbon fiber filament. So any radio signal can pass straight through the filament.
These are just the part drawings for Scout. Nothing much has really changed. Some quick status for Scout. Some completed tests, 3D printed models to make sure everything just for fitment. Lagner probe integration, XB communication stress tests, and FEA analysis on the tabs, which you were asking about in the email. Moving on, we've done the test. When we ran the test, we saw that it was inconclusive due to complex mesh parameters, and that there wasn't that much information about the material. We got as much as we can from the manufacturer. We couldn't really compare the stresses here, the bond stresses, to the yield stresses of the actual material because there wasn't information any on it. So the plan is that we print the Scout and we just do a physical test with the spring force, which should be 20 pounds. And if we see any deformation or any cracking or anything like that, then we would put those, would have like aluminum sleeves within those notches.
All right, and then this is the XB module test that we did. We did a clear line-to-line sight. This is the farthest distance we could get on campus, and that came out to be 1.16 miles. And then for test number 2, we tried to do a diagonal across different buildings, and this is the farthest distance we got before we got a little bit of it slowed down a little bit, and that was 0.14 miles, but that was between 2 concrete buildings. And then the status was highly successful. We simulated a code. We simulated code that we would expect to receive from Scout to Overwatch. And then we validated the XP RF module's performance and communication stability. The next phase, we will perform final communication range and signal integrity tests. Once the PPS Scout chassis is fully printed, we'll put all the RF antennas inside of Scout and on the placement of the board, just to make sure that it works.
So going on to the XP coding software and data dump, we obviously deployed and validated, as mentioned in the previous slide, the RF reliability transport Scout mission payload information to Overwatch within the flight window. We ensured the Arduino board has a micro SD card or nano SD card that with the reliable write speeds to keep up with the pace of incoming packet rates without serial buffer or any saturation or any polling effects that might occur. the results that came out that during the stress test, we continuously transmitted 400 plus SQL telemetry packets, IMU, temperature, humidity, etc., over 12 minutes, exceeding the expected revision window to further double down on our test. Then the single year, we achieved 0% packet loss at a close range and almost less than 2% at 0.14 miles because we had buildings and the concrete in the way. And then data integrity, the receiving Arduino successfully wrote all packets to the SD card with zero buffer overflow or file corruption. Next stages would be to conduct the final data dump test with Scout to enclose it in the PPS to verify the RF signal integrity through the composite housing.
The Langmuir probe testing plan. First, we were vacuum testing and testing of the housing materials, which was changed from machine aluminum to the PPS filament. We deemed that aluminum was not necessary. Going forward, we need electronics testing and software testing, which we will see through once the PCB boards are finalized, assembled. The first prototype of the Langmuir probe, 3D printed housing, features a peak block for the isolator. It's kind of the base, and we have 2 ceramic sleeves to ensure that there's no current leakage, and there is about 20 to 25 millimeters of exposure from the rods. We're going to figure out what is most optimal, and there's 0.2-inch spacing between the two. The final phase of testing for Scout. Between April 3rd and April 16th, we will be conducting deployment system testing, drop test, spring-loaded deployment test, integrated RF connection test, integrated Langmuir probe test, and PCB integration and full mission simulation test. Subsystem testing and integration with Overwatch. After finalizing the manufacture of Overwatch and Scout, we will integrate both systems and begin the deployment, RF, software, PCB integration, integrated Langmuir probe testing, and that will move us from 55% to 100%.
So for the electrical subsystem, I'll briefly go over the mission objectives. So we're capturing high-resolution transmission regions in the cold ionospheric plasma. For the power budget, we want to verify that the total current draw remains under 3.75 amps per TE line and to fit within the 1 ampere hour battery capacity provided. Mechanical constraints, just communicating with the mechanical team as well with the given constraints with the height, but that doesn't pose a real issue right now. So for the Overwatch CEO PCB updates, I've upgraded the PCB to a 4-layer stack up so that I can assign an individual ground and power plane to mitigate the stepper motor noise and improve the signal integrity for the modules in the Arduino. I have the chassis isolation, so I use modes for the signal isolation integrity within the optocouplers and pulled the power planes away from the mounting holes and border edge, just to make sure the board ground never touches the rocket's metal chassis. For the power domains, I clustered the 20-volt power and signal lines to one area in the board for noise reduction and separated the 3.3-volt plane in a clear middle island and the 5-volt plane everywhere else. And for quality of life, as requested, I added 2 LEDs and a reset button. This is the schematic, and this is the board. So the 2 LEDs are added here and the reset button here. Main reason for the added reset button is because the Arduino will be shielded and it's on the opposite side to maximize the space usage for the modules. And the reset button will allow us to access the reset button, of course. And as you can see, the thicker traces here indicate the 28-volt power line. And you can see the 3.3-volt island here and the 5-volt around, and the little moat designed around the optocouplers to isolate the noise within as it receives a signal from the connector. So this is just a 3D render of what it should look like. Some of these are blank because I don't have the 3D models of it, but self-explanatory. So for the Scout ISO PCB, I added an optocoupler circuit as well that communicates the first timing event. To activate the Scout, we want the Scout to be off until the first timing event, and the first timing event will go from the CEO board to the ISO board, and we'll activate it. And for these 2 boards in the ISO PCB, for the ISO, the Scout boards, we want to use surface mount components to survive the G-forces and impulses during launch. So this is a schematic for the ISO. It's similar to the CEO. It's just basically the flight computer. Just a very simplified version. It's just an Arduino Nano and 2 radios, XP, and the rock block. And this is the optocoupler just with signal and the regulators for modules as well. And this is a simplified board. Again, I don't have the 3D models of the board of the modules. For the Scout bias, So the Langmuir probe relies on a dual probe voltage sweep. So I implemented a transimpedance amplifier that anchors a 2.5 volt DC offset, so it captures the small return currents. So the architecture to protect the small currents, I implemented a fully surface mount, again, as said before, and this board is entirely dedicated to an analog measurement module. So just for risk mitigation, we separated the high voltage sweep generation from the sensitive receiver on the board, and we want to isolate this entire analog system from the noisy digital flight computer. So we want to ensure, of course, that the signal integrity is pristine and that it can survive under extreme conditions. This is a schematic. This is the triangle wave generator to bias the first Langmuir probe, and the second Langmuir probe will input the current into the transimpedance amplifier and give a safe reading for the Arduino. And of course, it connects through a connector for both cores as well. So this is the Scout bias PCB. As you can see, everything is entirely surface mount. Another thing I didn't know is the use of the coaxial cables. We wanted to make sure that the sensitive data, since the input current from the Langmuir probe will be very small, so we want to make sure that there will be no interference from any EMI interference or anything else. So anything, any interference will just be caught by the coaxial cable and be shielded to the ground.
Updated D-scope plan. Most of it is unchanged for Overwatch, but we have for Scout the removal of the heat shield. We understand that we're under the assumption that we're only going to be measuring while it's in space. Once it enters reentry, it's pretty much pointless. So we're not going to be using machined aluminum anymore. It's not necessary, and therefore Scout material has been changed to PPS filaments.
As for the MFSR plan, system verification steps before pre-simulation will include mechanical systems testing, electrical system testing, and software testing. For mechanical, we want to finalize a flight assembly of Overwatch and Scout, make sure everything is in flight configuration. As for electrical systems, we want to conduct full flight simulations, perform voltage stability tests on the Langmuir probe to ensure electrical isolation from the main chassis. As for the software, we want to finalize flight firmware on existing PCB hardware and validate the mission state machine. Make sure there's no synchronization errors once everything is integrated together in its flight configuration. Some success criteria: we want it to be completely autonomous execution from start to finish. So a full 15-minute mission timeline from launch deployment to reentry without any manual intervention or software hangs. We want to make sure we have data integrity. All telemetry from Langmuir probe and data from Scout must be successfully written on board with zero file corruption and transferred over to Overwatch. As for power resiliency, we want to make sure that the battery will maintain voltage and support all active subsystems simultaneously, even during peak current draws. As for initial plans for BBC May via Zoom, we want to integrate the hardware tour, show a live high-definition walkthrough of the Aero payload, highlighting the PPS GF20 structural components. Make sure we demonstrate a flight start, command, ground support equipment, ensuring it's in its ready state. We want to show the safety protocol of the worm gear, not back driving, making sure that everything is working properly, and then of course a full simulation of the Scout launching, essentially.
As mentioned earlier, summer test plan between April 3rd and April 16th for both Overwatch and Scout. Deployment system final testing, spring load deployment testing, locking cam node stress test, PCB communication testing, and then software full mission simulation. For Scout, deployment system testing, drop test, spring load deployment testing, integrated RF connection test, integrated Langmuir probe test, and then finally PCB integration and full sim test.
As for the Wallet testing plan, NJIT RockSat team understands that the following May 2026 testing and experiment era will remain fully integrated in the coral structural from June 2026 flight. We acknowledge that there will be very limited access to experiment once it's integrated and complete. As for the Wallops testing plan, minor changes have happened. We're still continuing the electrical system startup, RF transmission test, Langmuir probe operation test, Scout deployment testing, system data dump testing, and of course the Wallops structural test and full flight simulation as well. The minor change is we also want to conduct a full battery endurance test to confirm the power budget supports the entire flight duration of Scout. Once we're there, we're gonna bring spare batteries and stuff just in case we have issues with any batteries that won't pass this endurance test. As for our transmission test, we will verify the link between our transmitter and receiver using GSE2 or battery power during the timer event activated RF modules. We will still continue to test the Lamier probe operations and Scout deployment at Wallops. And this slide also has not changed. We will continue to do all this stuff. This slide also did not change from the STR.
All right, and then for travel plans, the team will be taking an NJIT van with 6 students and 1 faculty member, and the experiment on the 17th of May to Chickentee Island. Time to be determined by the check-in slot for you guys. And as for the budget, so far our total budget was $39,000. The budget left is $21,000. 15 of that is presumably for travel and hotels, so we're still within budget. And then for the estimated team size, initial plan was 6 students and 1 faculty advisor, and we understand that only 4 people will be allowed at Wallops facility per day. And as for project management, this does not change from since the STR. And then as for the timeline for the ISTR, this is not really changed from the STR, but let's go through it. Complete hotel travel details and book hotels and vans. Travel details are fully confirmed by the school. Hotels are being booked Monday. And then as for all the PCBs and hardware, that's mostly done. We're just waiting for final touches on the electrical side. And that's pretty much, this is all the same. As for parts procurement, parts in, we have the bar stock from Overwatch. It's already cut and welded. The step motor with the encoder is already in. The pro material is cut and fitted, 3D printed. 3D printer and supporting parts. We just bought a new printer for the club, so we can just print on site rather than waiting for the school to print for us. And then for most of the hardware most of it's stocked by NJIT. The other hardware we already ordered. For the parts that are not in, we're still waiting for the spring, some nuts, and shoulder bolts to complete the assembly. It's already ordered, should have been arrived today. And for the PCBs and electronics have not been ordered yet. And then any electrical installation for the Lamier probe has not been ordered yet.
As per request, an email for an inhibitor, we just had a small L bracket in front of Scout, just so if it does eject while we're doing tests, it won't fly out and damage anything.
As for conclusions, our biggest concerns include thermal and data resiliency, mechanical deployment, probe construction, battery dead on arrival, data buffer overflow or data latency, and of course, stepper motor reliability. Some plans to mitigate those concerns will be excessive deployment testing on both the spring system and the gear system, incorporate heat shield, but it will be possibly descoped. We'll talk about that further in the next slide. Once all parts are received, a more accurate weight up arrow will be provided, and we will be working with the physics students who have built Lamier probes for lab and consult with our advisor, Dr. Hyun. As for our next steps, assembly completion, we want to finalize the mechanical integration of all subsystems, logic burn and run, multiple simulations to ensure the system logic can perform all tasks successfully without any issues, a full mission simulation mid-April to execute. We're basically executing a full mission simulation from launch, trigger TE time events, and a full 15-minute flight to verify end-to-end data logging and deployment logic. We are going to finalize all designs and final placement for all components, including the antennas. And of course, now that we have the printer, will mass produce certain parts during extreme testing, and of course, finalize all aero in-flight configurations. We do have a few questions, but this is pretty much the end of our presentation. Do you want to ask?
Sure, yeah. Let's start with your questions, and then we'll go to Mike.
Yeah, so the first question is, we wanted to transition from Scout's body to a fully printed with the PPS. So I know before we were just saying the back end and the front top piece over here would be made out of aluminum. We're saying that both pieces, if we can, if it's allowed to have both of them made out of PPS.
Yeah, so I think that one, oh, sorry, yeah, I think that one is going to depend on what you find in testing. Again, I really want you guys to be successful and not break during vibe testing. And right now, I think that's my biggest worry. Your simulation, as you mentioned, was inconclusive, which is not great, but I think you have a great idea as far as just stressing it. So hardware rich, test it till it breaks idea, which will give you a lot more data than the simulation, even if it's more than the spring pressure. Keep in mind that testing that you're going to be going through, at least in the full z-axis, you're going to be seeing that 25 Gs, both sinusoidal pattern and that random pattern, but also in the XY. I think the XY has me a little bit more concerned just because it's going to be pushing on those tabs. But your idea about integrating some sort of metal reinforcement just in those key areas does add comfort as far as that goes. If you find that there are significant deformations, or maybe I am just a little bit paranoid at that point, but I think that is the biggest risk to your experiment. And I just want you all to be successful and be able to launch. So to answer your question in short, if you find that your 3D printed body, the tab portion, is not going to break under, the expected test conditions and expected launch conditions, to your best abilities of testing, I know simulation we pretty much exhausted at this point, then I would say that that would be a good avenue to go. I mean, you've tested it within reason, let's just say. If you find that it requires any reinforcements at that point, that's great to do. But again, I think I've illustrated my concern enough. I think, yeah, if you can prove to yourselves that that's not going to break and then relay that proof to me, and then I can be assured that you're not going to break, I'll feel a lot more comfortable for you. Let's just say that. So I guess that is an answer of that depends on your to be determined testing. Now, let's just say your testing goes fully according to plan and you're not able to break it, and you are very confident in those tab engagements, then I see no issue in 3D printing your whole casing for Scout. There'd be no reason why not.
Gotcha. Okay.
So just to kind of give you a little peace of mind, we will be probably doing like a hydraulic press test on Scout to see where it fails. Once we start printing itself. And the biggest concern, the reason why we want to fully print Scout is because the rock block needs a line of sight. And right now we're very limited on placement for the antennas and all the RF modules. They're kind of interfering with each other right now, so it hinders the rock block's placement. So kind of having the top cap of Scout being completely printed as well is just another easy peace of mind for us in terms of placement of the rock block.
Yeah, no, I think absolutely hydraulic press testing to really stress test those joints so you can get hard data on when they'll fail. That's excellent. And that would absolutely be a valid test for sure. That would also indicate, to your team whether you should move forward with that idea or if you're going to need to maybe go through a hybrid solution like you mentioned. But that's excellent to hear. I think that's a great path. Awesome to pursue it. There is limited time is the only other thing I would say. So just keep that in mind. I think you still have time. You just don't want to get caught in a scenario where you're trapped. You're trapped in one area pretty much.
Yeah.
But you're aware of that already.
We're also going to be annealing the Scout body entirely, so we'll be off gassing the body before it's integrated onto the sounding rocket.
Okay, perfect. That actually answered a different question that I had. I saw there were little metal inserts for hardware, and I was just going to ask if that hardware is going to be thread locked, and if so, if if the plastic has any bad interactions with said thread lock, as I've had some bad experiences with thread lock cracking plastic parts in the past. Long question, but it sounds like the answer is a yes. That hardware is secured through gluing.
Okay, yeah.
Our second question is, do you have any specific recommendations for the Langer probe voltage sweep parameters? We went from high voltage of 50 volts down to 10. Do you see any issue with that? Are we okay to do that?
I'm sorry. We went down to 5 volts. No, it's okay. We were looking at some documents. I think there was just a mix-up earlier, and we initially wanted to do a 50-volt sweep, but we were reanalyzing that, and we figured that the data won't be as clean if we did such a large sweep. So I made the circuit do a 5-volt sweep, but it can be adjusted to a 10-volt sweep if that is preferred.
Yeah, no, as far as a voltage, that's great. You're able to mitigate just that safety concern. It's not really a high voltage, but it is right at that threshold of what the user guide highlights. As far as quality of data, which I think is what your question is, teams have played around with the voltages for a few years. I don't think anyone's found the sweet spot, but 9 volts is common. So you're right at about that 10-volt range. I don't know if anyone's really centered on a specific voltage that is optimal, but I think if you were to go for that 10 volts, that would give you some indication that's not too low and you still have a pretty decent sweep range to be able to do. I don't know if that answered your question, but it's not really an answer that I think anyone's found yet.
Our final question is regarding the travel and integration logistics. Is our faculty advisor required to be present the entire integration trip, or is there some flexibility with the scheduling?
Yeah, we definitely do prefer that the faculty advisor is present for many reasons. They are essentially responsible for everyone at your institute. For one, there are scenarios we can work with teams on a case-by-case basis, so we'll just need to be aware, but our preference absolutely is that the faculty advisor is there with at least 1 or 2 students, 2 preferably.
Okay, perfect.
Awesome. Any other
Do
questions?
you have any questions for us? Comments,
That's-
concerns, or yeah, this is pretty much our end of our presentation. We do have the appendix, and then everything from the STR that we uploaded.
Yeah, no, totally. Yeah, I was just about to say, yeah, I forgot to hit the record, so we're gonna have to take it from the top again. Just kidding. No, but great work, everyone. I think, like I said, you've done a lot of testing. You've identified areas of improvement to optimize and maximize your chances of getting data back. I think that's great. I know there is a space constraint as well as a bandwidth constraint as far as frequencies being used and then used by other institutions, which I do have a couple questions here. Nothing that's going to stop anything, but we might need to switch your XP channel here, depending on which channel you're using or channel mask you're using. But overall, I think you are making great progress and your momentum is pointing you straight to FMSR at this point. A couple questions. Let's go to... All right, we're close to this one. So on 71, I think your mechanical inhibit idea is excellent. The question here is, once you're fully integrated, and we'll assume that that doesn't get removed until June, if that's a fair assumption, is it pretty easy to remove that plate or as an RBF procedure in June?
Yeah, it would just be bolted on. We could just loosen a bolt. Like you could loosen the nut. That'll be fine.
Okay, so just a nut on top and then
it's a
something
nut on
countersunk
top,
on the
yeah.
bottom?
Yeah, just a nut on top. You can just unbolt it.
Okay, perfect.
Yeah.
Yeah, definitely a good sanity check or sanity sake check. Have a mechanical inhibit. Let's see here. I think I heard somewhere around here, near here, swapping batteries. I don't know if that was before coming to Wallops. I remember you had talked about it before as well, just to identify the best batteries. But are you planning on swapping batteries at Wallops, or is this all before integration?
All before integration. We're just gonna do like a battery endurance test to make sure everything works perfectly fine for fully integration.
Got it. Perfect. That's the part I missed. All right, and then something that caught my eye. This may not be a problem. It's just something that randomly caught my eye on slide 54. Your coax connections. Those look like surface mount components to me.
Yeah.
I do have a concern that maybe it's not a problem, but that could be a lot of strain on those pads.
Mhm.
And it has a chance of not working the way you want it to. So
Oh.
question is, you might look into through-hole components, or you might find that you don't need them. But I figured I would just point this out. It's just something that caught my eye, but I don't see any specific problem with it.
Okay, I think in the 3D view it might have it might be too far back. I think I wanted to have it hanging off the board a little bit, and I think it should clip like in between the board, if that makes sense. Like there's from what I see from the 3D diagram, I can't really show it here because I can't change it, but it basically just inserts into the board. I think like when you look at the side, the whole like this cable part is clipping halfway through the board. So I think
I
there's
see.
with the footprint, but I think the connection should be fine. I only made it horizontal just so that there's no vertical. It's not taking up too much vertical space. But if I double check with them and the vertical space is fine, I might opt for a vertical connection instead.
Awesome. Yeah. No, it sounds like you're already thinking about it, but that's great.
Yeah.
Just one thing that caught my eye, but yeah, no, it's hard to tell from a 2D
Yeah,
view,
yeah,
right?
yeah.
No, great. And then as far as your reset button, let's see here that you added. I think we talked about it on slide 47. How easy is it to access once fully integrated?
I believe the whole PCB will be it will be closed off, correct?
Oh, do you want the reset button and like the LEDs on the outside of the submersible, or it being
I guess,
an issue?
yeah, I guess that depends on the second part of the question. um, what, I guess, when would you actuate this button? What is it resetting?
It should reset the whole Arduino. I believe if something would happen in the code. I was just asked to put a reset button. That's where I put it, but I don't know what the actual.
Got it. Okay, so it doesn't like in the middle, if we're doing sequence testing, you don't need to actually actuate that button at all.
No, it's not necessary. It's probably. I think it's just a testing. Feature.
Or reprogram later.
Or
Got
program,
it.
must be programmed later, because the Arduino is shielded, so it's on the bottom, so we won't be able to access the reset
So
button.
we need to reset button just in case anything fails.
Yes.
So that we can just access it. So we'll keep it as accessible as possible, but I think it shouldn't be a problem unless something breaks again.
Yeah.
It's only
Awesome.
to make sure the Arduino reboots on time, just in case any data dumping failing happens. We are trying to maintain redundancy, but there shouldn't be a problem.
Mm-hmm.
Awesome. So it sounds like just mainly a debugging feature.
Yeah, basically.
Okay, perfect. Awesome. Getting through here. I already got this one. This was the thread locker one. All good. And I just wanted to make sure, I think you all know your power allotment for your experiment section, since your half experiment is a ½ amp hour. And you also don't need to track any of Nebraska's power. You can track their weight. They'll probably be a little different as they're different, but really you only need to track the weight and power for your own experiment. They're their own experiment and they have all their own power. But main thing for this one is on slide 44, I think is where I saw it. Instead of that 1 amp hour, you're just a ½ amp hour. But that current limit, you're fine.
Okay.
And I believe we discussed actually in-rush current on the last one, which NNU now takes the lead as far as the amount of amperage they're going to take for that amount of time. But yeah, you were looking at like 65 amps for like 200 microseconds.
That was like the initial testing. I forgot what exactly we changed in the simulation, but it was more realistically going to be 27 amps. But it's very, very short, less than 50 seconds, so it shouldn't be too much of an issue. The fuse should be able to handle it.
Yeah, no, you'll be fine, but all good. All right, and then now we get to the fun stuff. This will probably take a little bit more coordination, but I've had a stab at giving everyone decent channel allocation. So question on your XB is channel utilization. In your FIR form, you had what was it? Yeah, okay, so you had a 5 megahertz spread of channels in the 2.4 gigahertz ISM band. Question is, have you chosen a specific channel yet?
Until we finalize the Scout and actually print it, and have everything integrated, you're still kind of in limbo until we can figure that out. We want to know how transparent this actual filament is, or the material is.
Okay. Okay, so I'll probably put this in a suggestion then, just because I'm trying to allocate everyone their own portion of the spectrum. There's just 3 other teams using 2.4 gigahertz, so it's not as bad as LoRa currently. But if you were to use channel 25, that lets, let's see, both. Okay, Virginia Tech could use 26. You would use 25, and then yeah, Alabama would basically stay where they are. They're between 2412 and 2452. So they're a little bit wider. They're 40 megahertz. It's very data hungry. But yeah, if you were to use channel 25 and test with that, and then give me feedback if that would work for you, that would be awesome. Also, if you need to use a larger bandwidth, I would need to know relatively soon here too.
Yeah, we should be printing Scout pretty much next week, Monday, since we already got the filament and everything. So we should be testing fairly soon.
All right, perfect. Yeah, I'll just make a note of that for the post-review summary email, just so we're tracking it. But yeah, no, just as soon as you know, well, the sooner you know, the better. Well, the sooner I know, the sooner you know, the better. All right. See, yep, the metal reinforcement idea is excellent. Yep, I got you no longer using high voltage. And I think okay, so I think this one we captured most of it, but I did forget to ask, which is the closest slide for you. Just on Scout, you mentioned there's some sort of structure that is not cradling it, but the guides that you're going to use for it. 2 questions there. Where Nebraska is, do you have any concerns about that standoff that's closest to you with the CAD model that they sent over, their latest one? I think where was the slide?
It's the integrated model, something like that. There you go.
I guess right here. Okay.
This one. Yeah, that bottom left standoff closest to Scout.
That wasn't. Are you saying like for clearance or?
Yeah. Does that make you nervous? Do you
No,
need
our
to?
current design, we didn't add it because it's not finalized. Add something that's not finalized, but
Okay.
we're just thinking of just printing something or that can like kind of surround it just to hold it more in place for the XY motion and the Z motion also. We can, since we're planning on it being 3D prints with the same filament, I don't think we always work around these holes here.
Okay, perfect. Yeah. No, I was just curious. On, I guess that was a 2-part question, right? But yeah, no, that support, and then if that support needed to have Nebraska shift over, which it looks like they might be able to. But yeah, if you find that you are running it up against a wall where Nebraska is, it looks like they have a little bit of room to move. Just let us know in that email, and I'm sure they're more than happy so long as their shelf space stays within the or the footprint of the actual experiment deck. But it sounds like you're already tracking all that, so that is great.
Okay, yeah, no, that wouldn't affect the top shelf. Maybe push this out farther, but I don't think it would.
Okay, awesome. Well, yep, that is all for my questions. I think, yeah, overall, like I said, great work. A lot of testing and a lot of testing in front of you. It's great to see that you've already started welding and fabricating the parts that you need. And then, yeah, just a lot of software and testing lays ahead of you. But I think you are on a great trajectory. Not only that, did you make a ISTR, but your FMSR is looking like it's going to be very doable. But that being said, let's go ahead and schedule your FMSR if there's no other questions.
Yeah. Let me pull up.
Cool. So that'll be the week of April 20th to the 24th. And if you wanted to do another Friday at 5 p.m. Mountain Time, that would be April 24th at 5 p.m.
Yep, I think that sounds good.
That sounds good for us. Yeah.
All right. Cool. And as usual, if anything changes with that, you need to make any adjustments to that time, just let me know, and we'll figure something out.
Right.
Awesome. Well, great work, everyone. It's great seeing everyone. It's great seeing all the progress you've made. And I'm excited to see all the things you find out as far as that 3D printed shell and your progress for FMSR. But if anything stands out, actually, we will be having more conversations with Nebraska just to get that exchange of parts for test parts so you can have actually something stand in for them. But in the meantime, I wish you luck on your FMSR preparations.
One question, Wesley. This is just for my welders that were asking that welded this. They wanted to know if their welds were NASA grade, especially for the spring. It wasn't in the slides, but he really tried his best. He's like, I really want this to be NASA. Like, they wanted NASA's approval, so I want to show it to you. Let me bring it up closer to the screen. What's your opinion on this? They just finished it late last night, and they're like, hey, show them the inside. The inside, I think, was my favorite part. They just wanted to get NASA's opinion. Is this NASA approved or not? I said, I'll let them know and see how it is.
Let me just say, it's a lot better than I can do. TIG welding aluminum is difficult.
No. It was, I kid you not, Wesley, there were some hiccups that we had, especially when you're trying to find the right heat settings and everything like that. So some trial and error, but it turned out pretty well.
I think it looks great. Yeah, that is not breaking anytime soon.
Gotcha. I'll let the welders know. Thank you.
Great work, everyone. That's awesome. All right. Well, everyone have a great evening and a great weekend. And if anything pops up, let me know.
Have a good one. Thank you, everyone.
All right. See ya.